And lo, there was much wailing and gnashing of teeth when people sat the AQA 2023 A-level physics exams. It went down as one of the worst set of papers that AQA have ever made, and to be honest, having a brief look at them at the time, I would agree with that. That was until 2024, but I'm going to cross that bridge when I get to it. So let's see if we can make sense of these questions then. As per usual, I can't show the paper on screen, unlike OCR and Edexcel, because if I do that, AQA will get the whole channel deleted due to copy strikes like they almost did in the past. Link to the paper and mark scheme are in the description for you. Question 1.1. Here we have a lambda particle that's making a pi neutral and a neutron. We're being asked what is the quark structure of a neutral lambda particle. Well, we're told that it's a baryon, so the baryon number is 1. We're told that its strangeness is -1. That's going to be the decider as to what it is here. First things first, we know if it's a baryon, then it must have 3 quarks. Some of them might be antiquarks, but the point is it's not a meson made up of a quark and antiquark pair. What else do we know? Well, we know that the charge must be 0 because, well, there's a 0 on it, so all the charges must add up to 0. So what do we know has to be in there? Well, we know that it has a strangeness of -1. And you can look up the table and just remember that strange quarks are strange. The strangeness of a strange quark is -1, whereas an anti-strange quark has a strangeness of +1. So in this case, we're going for just a normal strange quark. So we know it has to be S. What else do we know about a strange quark? It has a charge of -1/3, much like a down quark. Okay, so what else must we have in there to get the charge up to 0? Well, we can have an up quark in there. That's really the only thing that we have with a positive charge. Yes, I know we could have anti-down, but that's not going to work, and you'll see why in a second. So that brings us up 2/3. So now we have altogether +1/3. And so that means in order to get to 0, we must have another -1/3 charge in there to add up to 0, but it can't have strangeness because otherwise we'd have a strangeness that isn't -1, so therefore it has to be a down quark. So SUD, SUD, or usually the way that we write it is UDS. That's the quark composition of this lambda particle. 1.2. What interaction is involved in this decay? Now this is not an easy one. This involves strangeness, and we have to employ our strangeness rules. And what you need to remember is this, that strong can produce strangeness, but always conserved. Weak, on the other hand, strangeness is not conserved. We can say strangeness is destroyed. And it's worth remembering that total strangeness in a weak interaction can only ever change by +1 or -1. It can only ever change by 1. I don't think we're concerned with that bit in particular here, though, but we are concerned with the other parts of the rules. So we have a strangeness of -1 here. And we have here a pi 0. That has to be an up anti-up or down anti-2, equal and opposite particles, as it were. So strangeness is 0 here. And of course, strangeness for a neutron is 0 as well. So we're going from strangeness of -1 to 0 altogether. And so it looks like it's going to be weak because the strangeness is not conserved. And we can see that strangeness is destroyed and it's changing just from -1 to 0. It's just going up 1. So that checks out. So we can say it's weak as total strangeness, not conserved. And I guess that's it because we're only asked to state it. So that's 1 mark. And then we have qualified that as well. The mark scheme does actually mention the whole +1, -1 thing, but that's not really necessary in this case. 1.3, an antiparticle of the neutral lambda particle decays into a neutral pion and particle X. Identify X. Okay, so we're going, so we had this initially, and now we're going to have this. Man, I always do that. So that's going to be the case, and, oh, okay. Well, that's fairly easy actually, because this pion is essentially the antiparticle of itself, as it were. Because like we said, it has to be up, anti-up. And so if it's the antiparticle, then it would just be anti-up, up. And so that's essentially the same particle. And so nothing's changing there. So in essence, we're just going from UDS up here. If it's the antiparticle, by definition, it has to be the anti of all of those. And so, well, with the neutron, it's the nud and the pood. So this is up, down, down. And so, well, it's fair enough to assume that whatever particle this is just going to be the opposite as well. So that's just going to be anti-up, anti-down, anti-down. And that is just an anti-neutron. So there we go. Probably could have guessed that, because if one particle just decays into particles, then we know that the antiparticle is just going to decay into the antiparticles of those. So there we go. 1.4, we have the rest energy of a lambda 0 particle. So we can say E rest is equal to 2.6. Oh, sorry. We're given the frequency of what the photon would be equivalent to that. That's a weird way of writing it, but there we go. We have the frequency of 2.69 times 10 to the 23 hertz. And if that's a photon, then we know that the energy of a photon is HF. And so therefore, we're going to multiply by Planck's constant, and that gives us 1.78 times 10 to the minus 10 joules, but we're being asked for that in mega electron volts. Conversion factor for electron volts is 1.6 times 10 to the minus 19. We could convert after that, but it's worth remembering that a mega electron volt is just 1.6 times 10 to the minus 13 joules. So there we go. If we're going to be multiplying or dividing, well, we want a bigger number of mega electron volts, so we're going to divide that by 1.6 times 10 to the minus 13. And that gives us 1,113 mega electron volts. Let's put that to 3 sig figs. That's a tricky one. They've used 3 sig figs there. I've used 2 sig figs there, but I think in the formula sheet it is actually, let's just check. Yes, it is 1.60. So therefore, I guess we should give that to 3 sig figs. That's 1.11 times 10 to the 3 mega electron volts. Oh no, one of these wordy questions. I hate these. Discovery of particles made by a large international research team. Why? Well, it's because equipment is expensive. Or we could say, I guess, if we're talking about large teams, must require large number of man hours. Yes, sue me. To build and maintain. That's what I'd say. We could also say just a lot of time is needed to actually carry out the research, analyze data and that kind of stuff. You put whatever you want, you probably get a mark for it. Okay, question 2.1. What have we got? Bit of mechanics. World land speed record was 1230 kilometers per hour. We're going to have to change that into meters per second, I think. I tell you what, yeah, let's do that now before we do anything else. And so, well, let's just say that that is 1.23 times 10 to the 3 kilometers per hour. And so that is 1.23 times 10 to the 6 meters per hour. And then, well, if that's meters per hour, but we want meters per second, all we have to do is divide that by 3,600, which is the number of seconds in an hour. And so that gives us, it's close to the speed of sound. So that's 342. I'm going to go with 4 sig figs 2 for the time being. So 341.7 meters per second. Okay, we're going to need that in a bit. This is the average speed achieved by the jet-powered car in 2 runs. Each run was measured over a distance of, I should probably put S, shouldn't I? 1.61 kilometers. Or 1.61 times 10 to the 3 meters. Okay, the average speed for one of these runs was 343. Okay, calculate the time taken for the car to... Oh, what? What a weird question. So I guess we... the time. Okay, sorry, right. So we're essentially reverse engineering a mean speed. So the mean speed would be V1 plus V2 divided by 2. Fair enough. But we have the mean speed, which is our 341.7. Okay, but we're just looking for V2, let's say. And so therefore we just need to rearrange this, don't we? So therefore, mean V. Let's there's a posh way of doing it. We can do that. Times by 2, so I'm just going to say 2 times the mean V is equal to V1 plus V2, and so therefore V2 is just going to be equal to 2 lots of this mean V minus V1. And so, I mean, you see what it is, can't you, for crying out loud? There's only 2 values here, so we can just go below 343. You don't need to go through this whole rigmarole, do you? But whatever. So it's just going to be that 2 times 341.7 minus 343. And that gives us 340.4 meters per second. I don't know why they've got 340.3 in the mark scheme. That's going to be rounding error. They've probably just kept the 0.66666 in their calculator there. But whatever, we'd get the mark for this. And so therefore, if we're just looking for the time, then we know speed equals distance. Might as well just change that to d, seeing that we're not really using suva here. So therefore, time is equal to, just swapping those 2 around, we end up with time is equal to distance divided by speed. And so that is, well, let's just keep it at 1,610 meters divided by 340.3. And that gives us 4.73. Yeah, because we've been given the other speed to just 3 sig figs, so we will stick to 3 sig figs. That's not what I'm looking for seconds, aren't I? Just a note on sig figs, you will not get marked down, for example, using 3 sig figs when you technically should have given the answer to 2 sig figs. Really, the only time you'll get docked marks for that is in paper 3A, and even then, you'll only ever get docked 1 mark in the whole paper, even if you do your answers to the wrong number of sig figs significantly. And no pun intended, unless it's a question that says give it to the right number of sig figs. Slightly different. So there we go. Don't fret about it too much. As a rule of thumb, 3 sig figs is fine. Okay, 2.2, we have a graph and we have speed against, speed against distance. Oh yeah, speed against distance. Oh no, speed against distance. Ooh, okay. What's this going to represent then? So it goes up straight, blah, 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 comes down like that. Okay. Car reaches maximum acceleration when it's 5,600 meters from the start. So at a distance of 5,600 meters, what is the V? Let's just read off the graph real quick. So that's 450 meters per second. So this isn't a speed time graph, so just be wary that the gradient isn't really going to give us anything here. I don't think. I could be wrong. Let's see in a minute. Okay, the mass of the car is 6.5 times 10 to the 3 kilograms, so 6.5 tons. Determine the kinetic energy of the car at its maximum acceleration. Oh, that's nice and easy. Okay, so all we have to do is half mv squared it. So just reading off the graph for the time being anyway, half times 6,500, let's just do that, times 450 squared, and that gives us 3 sig figs. Yeah, let's go 3 sig figs. You understand why it would be 2 sig figs, because you're reading off the graph to 2 sig figs rarely, but there we go. So 6.6 times 10 to the 8 joules. That's a lot of joules. Okay, 2.3. Oh, what do you know? We are going to have to actually find the gradient. Okay, so acceleration is equal to speed times the gradient of the line. Okay, I guess that makes sense, because let's just check the units. Meters per second times meters per second divided by meters. And yes, those meters cancel, and so that does actually give us meters per second squared. I was wrong. Okay, so we're told that the power is at maximum acceleration, that's equal to 6. I'm going to put that in, well, let's say 640 megawatts. And so that is 6.4 times 10 to the, it would be 6, but now there's 2 more, so times 10 to the 8 watts. Okay, calculate the percentage of the input power used to accelerate the car at its maximum acceleration. Calculate the percentage of the input power used to accelerate the car at its maximum acceleration. Okay, so this is power input. And so we're going to need, if we're dealing with an efficiency basically, then we need power output as well. Okay, so how are we going to do that? We have, we don't have energy over time, so we're not going to worry about that. We do, however, have P equals FV. Whenever it comes to something moving, power developed, you might call it, we have P equals FV. This is just a divided by time version of the work done equation. It's just energy divided by time on the left, distance divided by time on the right, and that's velocity. We don't have a force though, but we can replace force with MA, of course. So P ends up being MAV. And so we know that that's equal to, because acceleration is equal to V times the gradient, so we can say that that is M times V times the gradient times V again. Or in other words, instead of half mv squared, it's going to be gradient times mv squared. Interesting. Okay. So we're told that we have the max acceleration at that 5,003. We've done that earlier, haven't we? So we're going to use this speed again, 450, and we just want the gradient. So let's say that the gradient is equal to something like, well, I guess we can just use what we've been told here, can't we? We can just use use those values. Yeah. Let's do that. So the gradient is going to be equal to the speed, essentially divided by the distance. Ooh, okay, so this might get interesting. So we might be able to take a little bit more of a shortcut. Yes, we could calculate the gradient just by doing that, but actually, if we just got our values here, and the v is going to be the same, it's going to be 450, then we can just say that this is equal to mv cubed, weird, over the distance. All right. Let's give that a go, see what we end up with. And so 6.5 times 10 to the 3 times by 450 cubed, and then divided by, what was it, 5,600. In fact, I'm going to replace that with 5.6 times 10 to the 3. And so I can just cancel those, top and bottom. Doesn't really make a massive difference, but hey ho, why not? So I'm just going to put 6.5 times 450 cubed divided by 5.6. And that gives me 105.8. So I'm going to say 106 megawatts. Okay. We're still not quite done because we have to figure out the percentage. So basically, I wish they would have just said efficiency, but whatever. So we have that input power. We have this output power. Let's just do it up here. So therefore, efficiency is equal to power out divided by power in. But we want it in a percentage, so we're going to have it times 100. So that is 106 megawatts. Okay, so they're both megawatts. So actually we can just ignore the megawatts. We can just say 106 divided by 640 times by 100. And that gives me 16.5%. 16.6%. There we go. That's our final answer. Question 2.4, messed this up the first time. Deduce whether the average deceleration is less than 3g. Okay, so we want the average deceleration. So I'm just going to say a hat. That's quite often how we represent a mean. We know from earlier that acceleration is equal to speed times the gradient of the line. So therefore we can say that the average acceleration is going to be equal to just the average speed times the gradient. And so if we're talking about deceleration, then we're talking about this bit of the graph here. So therefore, we're going to go from, let's say, that 470 divided by 2, 470 take away 0 divided by 2. That gives us the mean speed, the mean velocity. Then we're going to times that by the gradient of, let's have a look. Again, it's going from 470 down to 0, isn't it? So that's fine. So we can just say 470, that's our change in y, divided by, how long does it take? It goes from 8,000 to 15,000. So there we go. So we're going to say divided by 7,000. That's our gradient. And so therefore, we could just say that that's 470 squared divided by 14,000. And that gives us 15.8 meters per second squared. And so therefore that is less than 3g, so we are all good. Okay, let's try some electricity. Question 3. We have what looks like the simplest series circuit we can get. We have the EMF. That's essentially just total PT available to both resistors. We have R1, R2, and then of course we're going to have well, V1 and V2 across them, aren't we? We're asked to explain how the laws of conservation of energy apply. Consider the movement of 1 coulomb of charge around the circuit. Okay, fine. So we know that PD is equal to energy or work done per unit charge. So energy divided by charge, E divided by Q. And so therefore, energy is going to be equal to QV. So for 1 coulomb, what a weird question. So therefore, for 1 coulomb of charge, this is supplied an energy that is equal to the EMF by the battery or cell. Yes, I'm going to get them confused, sue me. And then we just say that this coulomb transfers energy to each resistor, and the energy lost is going to be equal to just QV. Therefore, we can say that Q epsilon, because that's the energy transferred by the cell, is equal to just QV1 plus QV2. Is that all I need to put? Yes. Yeah, that's fine. Yeah, they've essentially gone along this route here. So again, the energy lost in or transferred in R1 is equal to just V1 for 1 coulomb. It's just, why would they have it put in those terms? My days. What horrors await us next? 3.2. So we have this conducting layer and, okay, so we have the contact C. So it's basically just a variable resistor or a rheostat, potentiometer rather. So we have our battery there, and it is a battery this time, even though I'm not drawing it as a battery because life is too short. We have B there, A there, and we have C there, and then that's going there. And then we have our voltmeter across here. Okay. So we've essentially split this into two resistors, so V1 and V2. It's going to be the potential differences, and we can just say R1 and R2 as it were. We've created, in essence, two separate resistors. Okay, so what are we being asked then? So we have a 3-volt battery, and it has internal resistance. No, it's more complicated than I first thought. So we're going to have to pretend, as it were, that there is a little resistor inside of the old battery there. That is an R, not a V. After all these years, people still complain about my R's and V's, which is probably justified. The resistance of the conducting layer between A and B is 125. So we can say that R total, that is for the resistor here, not the internal resistance, is 125 ohms, not volts, you WASX science shorts. Okay, it's moved to end B of the variable resistor. Okay, so we haven't got two resistors, we just got one resistor that's 125. So if that's the case, then R is equal to 125 ohms. Switch is closed and the digital voltmeter reads 2.89 volts. Okay, show that R is approximately 4.8 ohms. Easy peasy. So we're going to crack out our EMF internal resistance equation, which is just, in essence, just a normal series circuit. It's just we have two resistors, but one of them just happens to be inside of the battery. IR plus IR. So what do we have? Let's have a check. We have that, and we're looking for that. So therefore, yes, we're going to have to find I, and every electricity question just comes down to V equals IR. So therefore, we can say that I is equal to V divided by R. Do we have V and R for a specific thingamabob? Yes, we do. We have it for the resistor here. So we're going to say that that's 2.89 volts. That's the terminal PD divided by 125 ohms. I don't know why I'm putting the units there, but whatever, it doesn't matter too much. And that gives us a current of 0.0231 amps. Let's go with that for now. And so then all I have to do is rearrange the EMF equation. But I'll tell you what I can do. I can just say V plus IR in this case, because we have V. So therefore, R is equal to EMF minus the terminal PD divided by the current. And so it's going to be 3 minus 2.89. divided by our current there. So essentially 0.11 divided by 0.0231. And sure enough, that gives us around, oh, it does actually give us bang on 4.8 ohms if we're doing that to 2 sig figs. 3.3, C is set to 1/5 of the distance between A and B. Okay, so it's gone up 1/5 of the way. So therefore, R1 in this case is going to be just that whole 125 divided by 5. And so that's just going to be 25 ohms. That's nice. And so R2 is going to be the rest of it. So 100 ohms, isn't it? Okay. Oh, we're told that. Then why did they tell us that? That's so silly. They could have asked us to calculate that. Whatever. Determine the voltmeter reading at this setting. Okay. That shouldn't be hard, I don't think, should it? Because the current is going to be the same, because the current is going through all of the resistor there. So it seems like a complicated question, but it isn't, because, well, we're just doing the same thing. I mean, can we not just say V equals IR? Is it as simple as that? So it's just going to be our same current, because nothing else has changed. We're just measuring a different amount of PD over a different amount of resistance. So times that by 25. Hang on, I don't even need to do that for crying out loud. All I have to do, if it's 1/5 of our total, then therefore we're going to have 1/5 of V total too. That is our 2.89. So all I have to do is 2.89 divided by 5, right? Yep. Weird question. There we go. I'd say that's a 1 mark rather than a 2 mark. There are multiple choice questions that involve 10 times as much work as that, but there we go. 3.4. Oh, we have a bunch of different thicknesses. Oh no, what is this? Oh, dearie me. Okay, so it goes across here, all the way to there. Okay, and then it's going, well, we have C there. Oh, I haven't left enough space. Okay, so it goes like this, and then it stops there. But then we've got a bit there. And then it's very thin there, and then it's just the same all the way across there. Okay, I haven't done a great job of that, but you get the idea. You can see it, hopefully. So we have A and P and Q and Q's just that. And then, we have the copper connector there. Right. So we're going to do that, then R there. Okay, cool. So 0 volts there, 3 volts there. So we're being asked to plot what will happen to the PD as we go across. All right, that should be fairly easy. But I know this caught quite a few people out because they somehow thought that the PD has to go to 0 at the ends or something like that. But we know that whatever happens, we must end up at 3 volts at B. And so that must be the case there, mustn't it? And we have to start at 0 over here. But the question is what's going to happen the rest of the way? I haven't really done it to scale, but that's okay. So Q as well. So P, Q, and then we have R as well. It doesn't really matter what the gradients look like, so long as you're being a little bit smart regarding when the gradient is bigger than the rest. So look, we have a thin bit here. So therefore, what do we know about that? Well, the resistance is going to be high. And here, if it's thicker, then that's going to be a low resistance. With Q, it's the thinnest that it possibly is. So R is very high for a second. And then again, it's going to be low here. And then because we have this copper contact here, we know that that's going to be R0 essentially. And so therefore, if we know that the resistance is high, then that means that the PD is going to be increasing very quickly as you go across a high resistance bit of the thingy there. So we're going to do this. So we're going to go like that. And then it's going to be a lower resistance. So we're going to have a less of a gradient. Oh, I don't think I've done a very good job there. So I haven't left myself enough room. Let's go for that. There we go. And then lower resistance. And then Q well, it's just going to like dip just for a little bit of a second. Not dip, it's just going to go very quickly because it's a very high resistance. So we're going to do that. And then we need the same gradient as we had to begin. Oh, no, sorry, not we had to begin with. So then maybe that's why I should have gone a little bit higher again. There we go. I should, to be honest, I could have gone with my first one, but there we go. So high resistance, so steep gradients, and then for Q we have that. And then, this confuses a few people as well, we can have the same gradient. Oh, look at that, nailed it. But what happens when we get to R? Because there's no resistance from R, because it's copper, so it's essentially zero resistance. We should just have a straight line because there should be no increase in PD. No resistance between R and B, no PD between R and B. So there we go. Okay, so the questions haven't been too bad so far, but question 4 is where it all starts to go a little bit wrong, especially at the end. So yeah, let's have a look at this. So we have just a prism. Is this going to draw it? It's not bad. Okay, so we have a light going in and then coming out. Boop. Okay. It's going in normally, so let's do it now. We have the critical angle, so theta C is 41.5 degrees. Okay, show that the glass used to make the prism has a refractive index of about 1.5. Let's start off with Snell's law. Why not? You can just use the ready-to-go equation that's in your formula sheet, but I like starting with Snell's law because you know you're going to have to use it anyway at some point, probably. So we might as well start with it. So yeah, critical angle, we're going to rejig this. If it's coming from air, sorry, other way around actually, this is going to be N1, this is going to be N2 because it has to be in the medium with the higher refractive index. And so therefore it's coming out of there. So we're going to say N1, that's what we're looking for. So I'm just going to drop the 1 and you'll see why now. Sine theta, 1 and sine theta, sine theta 1. We're going to change that for sine theta C because that's our critical angle. And N2, if that's air, then that's just going to be 1. And then sine theta 2, if that's going to be sine 90, then that's also going to be 1. So therefore, we can say that N is equal to 1 over sine theta C. And so therefore, we're going to say 1 divided by sine 41.5. And it does look like that's going to give us about 1.5. It sounds like a very common number that we deal with. Sure enough, that gives us 1.5. Okay, fairly easy. 4.2, explain why the ray emerges parallel to the incident ray. Okay, so no change in direction as it enters. Angle boundary after that equals 45 degrees. Therefore, also, or we could say both boundaries. There we go. Boundaries. So therefore, also exits normally to surface. So we have our normal there. Okay, we have our light going in, and that's theta there. And then we're going up like that. And then we're going like that. Okay, what is this? 4.3. Okay, draw on figure 8 the path of the ray as it continues inside the prism and emerges from the longest side. Oh, so it's going to bounce back. So if it's going to reflect there, let's put our normal in there as well. And we should try and keep it. Oh, that's pretty bang on, actually. I'm quite sure. Oh, I guess it is going to go out at, it's going to reach the bottom edge at the same angle as it did going in there. So I'm almost right there. Okay, and then it's going to refract out, but I don't think we're being asked that, are we? And emerges from the longer side. No, I guess we are. Yes, that makes sense. It leaves parallel to the original ray. There we go. So that's not too bad still. So this is for 4.3. But then we're being asked, when theta 1 is greater than theta here, some light escapes through one of the shorter sides. Show that theta is about 5 degrees. Okay, right. So we're going to assume, I think, that it's going to come out of here. And so therefore, well, we have 90 degrees here. This is 45 degrees here. We need to know what theta is if we actually have the critical angle here. All right. And if that's the case, so that's 41.5 degrees there. So above that angle, then light is going to escape, or rather less than that angle. I do apologize, other way around. Okay, so if that's the case, then that means that we have here 90 minus theta c. And so therefore, if I put that on there as well, that means that that critical angle there, so that's going to be theta c, 41.5. So this is going to be 90 minus theta c there. So there's going to be 90 minus 41.5. So this is going to be 48.5 degrees. Okay. So if that's 48.5 degrees there, then that's going to be 48.5 degrees there too. So if that's the case, right, okay. So we're looking for this angle here, and then we're going to have to do some use Snell's law with that. So we have here theta 1, and we have here theta 2. So if this is 90 degrees here, so we have a triangle here, so we're going to have to use our knowledge of angles in a triangle to figure this out. So theta 2 is going to be equal to 100 minus 90 minus 45 minus our 41.5 degrees there. Okay, so that is 45, take away 41.5 degrees, and so that gives us just 3.5 degrees. Okay, so we have our 3.5 degrees there. And so therefore we're looking for theta 1. And so cracking out Snell's law again, we're going to say that N1 is just 1, so that disappears. We're looking for theta 1, so that should be fairly easy. So sine theta 1 is equal to, what did we say it was, 1.5. Sine 3.5. And then we have to, of course, inverse sine that. So popping that into my calculator and inverse signing that, or arc sine, whatever you want to call it, and that gives me 5.3 degrees. Pretty tricky, that one, just because there's a lot of moving parts going on there. You're dealing with 1 and then 2 and then 3 different points where the light collides or is incident on the boundary. Still not the most difficult part of the question, though. The next bit is even trickier, if I remember rightly. Let's have a look. Manufacturer wants to make a prism with a larger value of theta. So we want theta to be greater. Two alternative changes. We have number 1. Okay, so we have an equilateral triangle, same refractive index and same shape and smaller refractive index. Okay, discuss whether either of these two suggestions would work. Not an easy one. Let's deal with the first one. We have an equilateral triangle. Bang on, well done me. First issue is that light wouldn't come out at the same angle. Because this is now 60 degrees as opposed to 45, then light wouldn't come in and then bounce off, and then, well, it would refract out at this second boundary. So let's just say light will not be reflected back at same angle. But we have probably a bigger problem, and that is light would refract out on the second side, let's say, on the right side. Personally, I think it's a little bit mean to ask you that without getting you to do a calculation, because it's a little bit difficult to eyeball that one. Second one then, we have the 90 degree one there, and so light is still going to come out, that's fine. But if we have a smaller refractive index, then we saw earlier that refractive index is equal to, we saw earlier that, well, rearranging it, sine theta c is equal to 1 over n, so therefore a smaller n, therefore if n goes down, theta c increases, so the critical angle would increase. And so that would mean, going back up here real quick, so that means that if this angle here increases, then that means that, let's say that it increased to, say, 42 degrees. Then this 41.5 degrees would now be too small. for it to be TIR'd, light would actually come out if it was at this angle. In order for light to still be TIR'd at this point, what would need to happen? Well, we would need the angle here to increase, which would mean that, well, if the angle there increases, that means that the angle there must decrease. This angle must decrease. And so that means that this angle decreases. So if that's the case, then that ultimately means that this angle going in here would also decrease. Therefore, theta at boundary, or let's say theta when entering, decreases. Is that what we want? What do the questions say? It's been so long, I've forgotten. To make with a larger value of that. No, so neither of these would work. Yeah, not a nice question, that one. If it was me doing the exam, I'd definitely leave that one until the end. 5.1, we have some Young modulus goodness. We have a stress-strain graph, so we have stress there and strain there, and the line is going up and then just curving over a little bit. Okay, determine the Young modulus of the metal. Of course, we just want to use the linear portion of the graph, and you should find that, well, Young modulus is equal to stress over strain, and so that's equal to the gradient here, and so that should end up being something like 1.4 times 10 to the 11 and the units pascals, but there is a little bit of leeway there, but not much. 5.2, how is the metal brittle? Well, that's because there's very little increase in strain before breaking, or we should probably say past the linear mode or linear portion before breaking. I nearly said accidentally, oh, there's very little plastic region, but just remember that just because the line curves over a little bit, that still doesn't necessarily mean that it's plastic. It still might be elastic. So we need to talk about the linear portion of the graph. 5.3, okay, this is where things get very tricky. This is possibly one of the hardest questions, or is it 5.4? Yeah, it's 5.4. 5.4. Oh, yeah, let's worry about that in a minute, shall we? So we have a bar there, have a light that is coming off that. Is it in the middle? Yeah, it is in the midpoint. That's handy. And we know that we're going to have the weight of the beam as well, probably. Okay, and we have A and we have B. The unloaded length of each steel wire was 1.2 meters. Okay, so L is 1.2 meters. Fine. Mass of the lamp, 16 kilograms. And so therefore we can say the force down here is 16 G, not 16 grams, 16 times G. Distance between wires is 2 meters. So, well, we can just say that this is going to be 1 meter. Because that's probably what we're going to have to do, because we're going to take moments, aren't we? Diameter of each wire is 0.8 mil. So I'm going to say that's 8 times 10 to the minus 4 meters. And the Young modulus of the steel is 2.1 times 10 to the 11 pascals. All of these are to 3 sig figs, though, so we can give, apart from the mass, whatever, I'm still going to give my answer to 3 sig figs. Calculate the extension of each wire. Interesting. Oh, do you know what? I don't think we actually do need to take moments in this case, because everything's nice and even. So we can just say that force going upwards equals force going downwards. So tension equals the weight. So therefore, we're going to say the weight is equal to 16G plus, mass of the bar is equal to 4.4. There we go. Okay, so so the weight is 16G plus 4.4G, and so that is just 20.4 times 9.8, isn't it? So 20.4 kilograms times 9.81. Let's be accurate, shall we? Okay, so 20.4 times 9.81, and that is pretty much 200, but let's just say, yeah, why not? Let's just say 200 newtons. Cool. And so what we can do, in fact, is just combine all of these. So let's just write down the Young modulus equation. E is equal to FL over A delta L, or you might use X. Do you know what? I'm going to use X. I don't like using delta L. And what are we looking for? We're looking for X. So therefore, we're just going to swap around these two. So X is equal to FL over AE. And so that's going to be 200 times our original length of 1.2 divided by the area. Now the area is equal to pi d squared. over 4, so pi r squared. However, because we've got 2 rods, I'm just going to combine those. So in essence, we've got double the cross-sectional area, which is perfectly acceptable to do. So I'm going to say 2 times pi d squared over 4. And then I'm going to times that by the Young modulus, which is 2.1 times 10 to the 11. Of course, I can just cancel this a little bit, so 2 divided by 4, so I'm just going to put that on the bottom. And actually, if I've got a divided by 2 on the bottom, then I can just put that on top there. Isn't that handy? So I'm going to say that that's 400, I'm just combining those two, times 1.2 divided by pi times 8.4 times 10 to the minus 4 squared times by 2.1 times 10 to the 11. Popping that all into my calculator, and I end up with 0. Let's put it in standard form. There we go. So 1.137, but let's just say that that is 1.14 times 10 to the minus 3 meters. So just over a millimeter. Okay, 5.4. Possibly one of the trickiest questions I've ever come across, because it involves 3 separate ideas that you have to use. So this beastie 5-mark calculation. Here we go. So I just copied that bad boy, and we want to find out what x is there. Okay, we're going to need that data as well, actually. So let's grab that. The thing we need to realize, first of all, is that we have the actual lamp at a different distance. So I'll tell you what, I'm just going to delete that. We want to know where x is. I don't know which side x is going to be on right now. I probably could figure it out if I looked at the question for a second, but there's our lamp there. So that's x equals question mark. But we still have the weight of the beam pulling down there. And so that's going to be, I'm just going to call that weight of the bar. So this wire here has been replaced with aluminium, which is going to have a different Young modulus. But the original length is going to be the same. So therefore, if you pop the lamp in the middle, then it's not going to be straight. It's not going to be horizontal. We need to make it horizontal by shifting that lamp. So where do we put x in order for that to happen? We are given the Young modulus for the aluminium as well, which is nice. And so that is 7 times 10 to the 10 pascals. This is one of those times where you have to really, really, really think hard. With these kind of calculations, you have to, first of all, just consider what is staying the same and what is going to be different in both cases, or what is going to be the same and different for both wires. So let's just have a think about that for a sec, shall we? So if it's going to be horizontal, the extension, oh flip, we've got x now, don't we? I'm going to use delta L then. Delta L is same for both wires. So what else is staying the same? Until the diameter is different forward as well, actually. So the diameter is going to be 1.2, does it say? Sorry, 1.6 times 10 to the minus 3 meters. Okay, so double the diameter of the steel wire. Let's have a look at our equation again. So FL over a delta L, I'm going to use that now. So delta L is staying the same. A is going to be different, or rather D is going to be different for both. L is the same for both, but force is going to be different for both as well. And so therefore, we can actually treat this as a proportionality problem, or at least part of this question we can anyway. So we can say that the Young modulus is proportional to F over A, and that is going to be handy in a minute. In fact, we can go one step further because we know that A is equal to pi d squared over 4, we can say that therefore Young modulus is proportional to F over D squared, and that's going to be even handier. So we're going to have to take moments about a point, aren't we? So I'm going to take moments about A. So what do we have going clockwise? Well, we have the force due to the lamp going clockwise, we have the force due to the weight of the bar going clockwise, but then we have the tension in the wire B pulling anti-clockwise, don't we? And so therefore we can say that 16gx, and that is the force 16 times g times the distance. So this is the moment due to the lamp, plus, what was it, 4.4 g just times 1, because it's just 1 meter. So actually I'm just going to just drop the 1 there. And that is equal to 2 lots of the force on B, isn't it? So I'm going to say 2Fb. So the problem is now, well, how do we find out what this force is? Well, we can't really know that directly. So chances are we're going to actually have to think about forces as well now, just forces up and down. So what we can say is that the forces pulling upwards are Fa plus Fb. And what are they equal to? Well, they're equal to the weight of the bar and the lamp, just like earlier. So that was 20.4 G, wasn't it? That's just the 16 kilograms plus the 4.4 times by G. But again, that doesn't really help. Us too much because we don't have the force due to A, do we? But we can know what the force in A is in terms of the force in B. How? Well, it's because of what we've written down here. If this is true, then this means that force is proportional to the Young modulus times d squared. So I should probably call these B instead of A, because that's confusing actually, isn't it? So I'm going to call this A and B. There we go. So B is our aluminium, isn't it? Aluminium. And this is steel. Okay, we can say therefore that the ratio of the forces for both wires is just equal to the ratio of what they're proportional to. So Young modulus times the diameter squared divided by Young modulus times diameter squared for the second one. We now have, in essence, two separate ratios. And so we're going to say EA over EB times by, I'm just going to square it all at the end there. So dA by dB all squared. I think this is really mean because if they'd just given you a one marker before this question that said, give FB in terms of FA, or vice versa, then you could have done that. And then the rest of the question would have been really easy. It's the fact that you have to infer this in a beastly 5-mark question. It's one of those things that you either get probably 5 marks or probably nothing. Because it took me a few minutes to figure out what was needed. But I'm thick, so there we go. So what do we have? I mean, the giveaway here really is the fact that if you look at the numbers, look at the diameters, one is double the other. Look at the Young moduli, one is triple the other. And so the fact that they've given you nice multiples for the data, well, that should indicate to you that there's probably going to be some proportionality employment in here somewhere. Okay, so EA divided by EB, we can see, you can put the numbers in if you want to, but we can see that one is 3 times the other. So I'm just going to say 3 divided by 1, and so, well, that divided by 1 just disappears, doesn't it? Then I'm going to times that by the ratio of the diameter squared. So dA, we can see that that is half the size of dB. So therefore I'm going to say half, but that is squared. And so essentially what we have is 3 times a quarter, or in other words, 3/4. So therefore F over FB is 3/4. So we can say FA is equal to 3/4 FB. Now we can pop this back into here. So we can say 3/4 FB, replacing that FA, plus another FB is equal to 20.4 G. Or in other words, 7/4 FB is equal to 20.4 G. Rearranging this, just taking the 7/4 over the other side, so that means that FB is equal to 20.4 G times by the reciprocal, so times by 4/7. And that gives us 114.4 newtons. Let's stick being accurate for the time being. Now that we have that, we can pop this FB back into here, and the rest should be fairly easy. Taking this down here, first of all, well, we want to get rid of the G's to the other side, so let's just divide by G all along. So 16x plus 4.4 is equal to 2 lots of 114.8, so I'm just going to say 228.8 divided by G. I'm just going to leave it as G for now. And then if we want to get the 4.4 to the other side, just minus 4.4, and then get the 16 to the other side, just divide the whole thing by 16. And that gives you 1.18 meters. That's one of the trickiest questions I think I've ever seen in an A-level paper, because there's so many inferences that you have to make. But like I said, just bear in mind that proportionality, thinking about what is staying the same, what's different, is a really powerful tool to have, especially when you're stuck. Okay, on to greener pastures. Here we have a pencil that's oscillating up and down. We have the force of the resultant force at any given time is equal to the area times the density of the water times g times y, where y is the displacement at any time. Okay. Pencil is pushed down and released. It then oscillates, so that the pencil moves with simple harmonic motion. Okay. How do we do that? Well, if it's simple harmonic motion, then we want to prove that A is proportional to displacement, don't we? Oh, is that literally it? I think that's it. So in this case, therefore A is proportional to Y. And we can say this is true. It's only proportional to Y. This is true because rho and G and A, rho and G and A, let's put a comma there, are constant. So there we go. Why can they just use the X though? It's to confuse you, of course, because they're big meanies. We have the pendulum equation. Huh, interesting. So it works for this too. Well. Okay, the measured value of L is 85 mil. Okay, so let's say 0.085 meters. And the pencil is pushed down 5 mil. So y is equal to 5 times 10 to the minus 3 meters. And we're just being asked for the acceleration. Fair enough. So we know that, the maximum acceleration, sorry. So A max. So we know that acceleration is equal to minus. We don't really care about the minus because it's the same both sides. So we're just going to say just omega squared x, or y in this case. Yeah. And so therefore we're going to say that that's equal to 2 pi f all squared times by y, but we don't have the frequency here. We have got the equation for time period. So we're going to pop that in instead. So that's 2 pi over t. That's all squared times by y. Let's just multiply that out. So 4 pi squared divided by t. I think we can probably be a bit cleverer with this one. I think so. I forgot to square that. Whoops. So that's equal to 4 pi squared divided by the whole t squared thing. So that, again, that's divided by 4 pi squared, because if we're squaring, so t squared is equal to 4 pi squared times by L over G, essentially, okay? So then times by L over G, and so we need that y on the end there. And so, wow, everything cancels. That would be kind of weird. So 4 pi squared cancels. That G on the bottom ends up being on top. So therefore, are we literally just looking for YG over L? That would be kind of weird, but that would be kind of cool if it worked out like that. Let's have a look. So what do we say it was? 5 times 10 to the minus 3 times by 9.8 divided by 0.085. Could use power to 10 there, actually. Let's just keep it as that. So 85 times 10 to the minus 3. Cancel those. And so we end up with 5 times 9.81 divided by 85. And what do you know? We end up with 0.577. Let's just get that to 2 sig figs. 0.58 meters per second squared. So everything did cancel out nicely. There we go. 6.3, a floating pencil is just like a ship, apparently. Waves cause forced oscillations. In certain conditions, resonance may then occur. Explain what is meant by resonance. So there should be one that you should have locked and loaded, ready to go. Resonance is the increasing amplitude of oscillations. Due to the frequency of driving oscillations. Oh, that says driving. Fine. Driving oscillations being the same as that, or being equal to, let's just say, being equal to the natural frequency of the system. I'm surprised this isn't a masking, because usually they really pick up on this frequency of a lightly damped system. You don't really need to know why. So there we go. Masking does say that the amplitude is at a maximum. Amplitude of oscillations being at a maximum, fine. Guess we could put that, because if we have the graph of oscillations compared to thingy, we are talking about there, that's resonance. Maybe I would have lost a mark there. 6.4, what do we have? We have a boat and we have waves. Oh, no, this looks complicated. So the wavelength is 118 and the waves, C for the sea. And we know that the boat is moving at 8 meters per second. All right. What are we being asked then? Natural frequency is let's say F0 is 0.13 hertz. Crew member needs an emergency operation. My days. Sounds like a level of surgeon simulator. Ship's doctor is confident that she can do the operation. Blah, blah, blah. Okay. Car. Way to add a bit of drama to the question, eh? Got to make it interesting. Can't just be like, hey, what's going to happen? No. It's like an episode of House. Stop the ship's motors and loosely anchor the ship to the seabed. Continue to sail at that speed in the same direction. Deduce which is the better option. I'm going to guess that it's going to be, keep going, because that's like what it would be if it was a TV show. Be like, should we weigh anchor? No, the only option is to keep going. Okay, so what do we have? We have the wavelength and the wave speed for the waves. So therefore we can say the frequency of waves, that's something that we can calculate, and we do need to calculate, is equal to, because V equals F lambda, or rather C equals F lambda. So therefore F is equal to C over lambda. So that's 14.2 divided by 118. And you end up with a frequency of 0.12 hertz. Okay. So if that's the case, then I guess we could say that if we stop, the frequency of the waves is similar to the frequency, the natural frequency. Therefore, some resonance may occur. Oh, I think I'm right about this. Okay. If keep going, if moving, he goed and goed until he went. That's a deep cut right there. Okay. If moving, then that means that the wave speed is no longer going to be 14.2, because we now have a relative speed, don't we? So that's going to be 14.2 take away 8 meters per second. So that's going to be 6.2 meters per second. Yes, because... Oh, wait, does that even work? New frequency is equal to 6.2 divided by 118. And so that would give us 0.055 hertz. So, yes, that would be very different from F0. Therefore, no resonance occurs. I think it's safe enough to say. Therefore, safer. There we go. Do we need to go down the road of, amplitude would be less, oscillations would be less? I don't think we need to. I think we can infer that. That's pretty much implied. Okay, multiple choice. Way better than any of the other stuff that's come so far. So, question 7. Which combination gives a distance travelled of 1 millimeter? Okay, so we're just looking for just 1 times 10 to the minus 3. That's what we want, isn't it? So let's look at A first. So of course we know that distance is equal to speed times time, so we just need to multiply both thingies. So 10 micrometers, that's going to be 10 to, well, we're just looking for that, aren't we? That's going to be 10 to the minus 6, but it's going to be minus 5 because there's 10 of those, and times 100, so that's 10 squared, and so that's, I think that's going to be our answer. Yep, I think that looks about right. Yeah. Is it worth checking the other ones? I think you can check the other ones yourself. Yeah, fine, let's do it. So 10 to the 3, but that would be 10 to the 4. And then times that by 10 to the minus 6, minus 7, minus 8. So nope, that's not going to give us minus 3. That's going to give us minus 4. C, 1 nanometer. So that's 10 to the minus 9. Times by 1 giga. So that's 10 to the 9. So that's just 1. And then we have megameters per second. Nice. So that's 10 to the 6. So that's 10 to the 5. Times by 100 nanoseconds. So that's 10 to the minus 9 up to minus 7. And that's going to give us 10 to the minus 2. So neither of those are right. Question 8. We're jumping as high as we can. What's a reasonable estimate of her speed just after she leaves the ground? Okay, so we're going to have to use conservation of energy here, methinks. So we know that mgh equals half mv squared. I have no idea what speed we're looking at. So therefore, all I know is how high does a person jump off the ground? I'm going to say height equals 1 meter. That sounds about right. For a normal person, probably about 10 centimeters for me these days. Cancelling the m's, we end up with that, and we're going to say that v is equal to the square root of 2gh, and so that's equal to the square root of 2 times 10, let's just say, times by 1. So in other words, the square root of 20, and that's 4 point something something. So I'm going to say that the answer is B, and the mark scheme concurs. Question 9, we have neutrons N, protons Z. Which combination gives the greatest specific charge? Okay, so specific charge is just the same thing as charge to mass ratio. So that's Q divided by M. So that's what we're looking for. The biggest one of those. It doesn't matter what they are, we're just looking for the biggest number, aren't we? And we know that, well, let's have a look at A first, shall we? So A, that's going to be, well, 5. Divided by, what's the total mass? It's going to be 11, because it's protons and neutrons. That's what gives us the mass. We don't need to convert anything because it's all relative. Let's just look at the others real quick. So we have 7 divided by 15. Oh man, I don't know off the top of my head. Do I? It's been ages since I've done GCSE maths. So 13 over 29. I don't think that's going to be the case, is it? That's not going to be one, I don't think. And then we have D as well. It's going to be 17 over 37. Definitely not going to be that. So is it going to be 5/11ths or 7/15ths? I can't. I really can't do that in my head. So that gives us 0.45. And okay, to be fair, they are very, very close. So I think the answer is B. I don't feel too stupid now. 10. What's true about muons? A. So muons we're talking about. That's not how you write muons. Muons. Okay, so A. Quark, anti-quark? No, of course not, because they're fundamental particles. They're not hadrons, they are leptons. B. They include pions and kaons. What are you talking about? They're mesons too. This is going to be an easy one. They are subject to the strong interaction? No, because they are leptons, not hadrons. They're subject to the strong interaction, leptons weak. D. They decay into electrons? Yes, because they are essentially heavy electrons. Yes, I've missed out the neutrinos there. That is not a full answer. 11. We do have a Feynman diagram. People said that they disappeared, and I said, no, they haven't, and they didn't believe me. Always believe me. That's a lie. So, what are we being asked? What is... Oh, what's E, F, and G? Oh, that's easy. Look, it's an antineutrino. You should know off the top of your head that whenever we get an antineutrino release, or in this case anyway, it's beta minus decay, just normal beta decay, so that should be an electron there. And we have a nud turning into a pood, because we're going from we're losing a negative charge, as it were, in the electron. So, we're not talking about those, are we? We're talking about quarks. Pants. Okay. I mean, that's okay. Like I said, neutron is up, down, down, the nud, and proton is the pood. And so therefore we have a down quark turning into an up quark. And so it looks like the answer is going to be B. And if you really didn't know how to do that, well, just look at the lepton number. For the anti-electron neutrino, it's going to be -1. So whatever is made here must be +1. And so it has to be an electron, doesn't it? Photoelectrons, we have a photon energy of 4.2 times 10 to the -19 joules. Okay, work function is 2.4 electron volts. We're going to have to convert. What is the maximum speed of the photoelectrons? Okay, so seeing that we're dealing with speed, we have to go for joules, don't we? So it's worth converting the electron volts into joules this time. So we're going to multiply that by 1.6 times 10 to the -19 to get the number of joules. I think we could probably just do 2.4 times 1.6, and that gives us 3.84 times 10 to the -19. And so therefore, well, let's get our equation now, shall we? EK max is equal to HF minus phi. We don't care about HF, it's just the energy of the photon in this case, which we have. That's right there. And so therefore, we're going to say that that is just the 4.2 take away 3.84. So that gives us 0.36 times 10 to the -19 joules. There's no point putting that in for no reason. And that's equal to half mv squared. So therefore, speed is equal to the square root of 2e over m. So that's equal to the square root of 2 times 0.36 times 10 to the minus 19 divided by the mass of an electron, which is 9.11 times 10 to the minus 31. Don't think I'll cancel any powers here. And we end up with very fast electrons that are booking it at 2.8. I'm going to see what the answers has that, but whatever. 2.8 times 10 to the 5 meters per second. So I think the answer is C. Question 13, electrons with kinetic energy pass through. So we're talking about electron diffraction. A change is made and the second pattern is produced. Okay, so we can obviously see that the wavelength has increased because okay, fine, let's go one step back. The angle has increased, hasn't it? And you know that from just generally with diffraction, but especially if we talk about, our d sine theta equals n lambda, we know that sine theta is proportional to lambda. So let's have a look at these then. So A, decreasing the kinetic energy of the electrons. Okay. Okay. So we need to employ de Broglie's equation as well. So lambda is equal to h over mv. If kinetic energy goes down, then that means speed goes down as well. If speed goes down, looking at this, that means that wavelength goes up. So if wavelength goes up, then therefore our angle should go up as well. So A looks actually pretty correct to me. Let's just look at the other real quick. So B, placing the electrons with protons. So if they're protons, that means that the mass has gone up. Oh, same kinetic energy. So here's half mv squared. If that goes up, then that means the speed goes down, but the speed goes down by... Oh, man. This is a tricky one, actually, but fine, let's do it. We're talking about... We have de Broglie's equation here, and that's h over mv, isn't it? Momentum. But the problem is that if we're talking about kinetic energy, then we need to put kinetic energy in there. And sometimes you will need to do this. So let's just have a look. We know that E, kinetic energy, is equal to half mv squared. And I think this equation is in the turning point section, actually, so you don't need to remember it, but it is useful to know where it comes from. All I'm going to do is multiply both sides by m, and so therefore we end up with me is equal to half times momentum squared. So rearranging this for momentum, we end up with P is equal to the square root of 2 times the mass times the kinetic energy. So therefore, wavelength is equal to h over 2me, the kinetic energy. So if that's the case, and they have the same kinetic energy, then that means that if the mass goes up, then the wavelength goes down. So that cannot be true. Let's just look at C, using a sample with wider spacing. So if D goes up, then that means that the angle needs to come down. So that's not true either. And then finally, moving the screen closer. Well, no, because if you move the screen closer, then they don't spread out as much, do they? So the angle is going to stay the same, but the fringe spacing, as it were, we're talking in terms of Young's double slit, that's actually going to go down. So we'd see the rings closer together, wouldn't we? Okay, 14, we have a graph. What are the wavelength and frequency of the wave? So first things first, we can see the time period is 6 milliseconds, or in other words, 6 times 10 to the minus 3 seconds. So therefore, the frequency is going to be 1 divided by the time period. So 1 divided by 6 times 10 to the minus 3. And that's going to be 0.17, isn't it? So it can't be B or C. And then finally, we just want the wavelength. We're given the length of the string. Ooh, okay, this is actually a little bit trickier. Oh, my days. No. Hang on. The diagram shows the displacement time graph for a pointer string. For the second harmonic, this is the second harmonic, then it literally is going to look like this on the wave. Okay, so that's literally just one wave. Yes. So if that's 1.2 meters, that's the wavelength too. So the answer is going to be C. They called it a standing wave. Well. Oh, are you kidding me? I leave teaching, and for 14 years they would say it's a stationary wave, not a standing wave. I think somebody got told off for that because they said you shouldn't call them standing waves. Whatever. Standing wave, I much prefer calling them standing waves. It's old school. What statement about the two waves is not correct? They have the same frequency. They must have the same frequency, so that's not true. B, they have a constant phase relationship. No, because that's to do with coherent waves. We wouldn't have the string going up and down if they had a constant phase relationship, so that's not true. They travel in opposite directions, they have the same speed. Yes, that has to be true because they're on the same piece of string. Constant phase relationship, that's for coherent light. That's to do with lasers. That is not to do with standing waves. Ooh, feels good saying standing waves. 16, double slit. We have this, so let's write down Young's double slit equation. Why not? Lambda d over s. Okay, what do we have? The distance is changed to d half, so this is halved. Which combination will produce a fringe spacing of 1.5 W? All right. All we want to do is actually just multiply these numbers as they are in the equation, because even though W is equal to all of those, it's true that it's just also proportional to all of those things. And so if we're looking for an answer in terms of W, that's all we have to do. So we're just going to take our lambda in terms of lambda, so 0.66. We're going to divide that by 2 because that's what's happening here every time. And then we're going to divide that by the new slit separation, 0.22. And so there's going to be 0.33 divided by 0.22. And that is bang on 1.5. And so that looks like that's going to be our answer. Should we check B just in case, just to show you what it looks like if it's wrong? So 0.75 lambda divided by 2 again, divided by 0.5. And actually those are going to cancel because that's a half and half. That's not going to be the case, and you'll find that with all of the rest going down. 17, single narrow slit. Okay, diffraction pattern. The slit width is increased. Okay, so again, similar to the electron diffraction question, we can just use our general idea about this. We don't need n because we're just talking about a single slit, so we're just going to say it's proportional to that. There we go. We know how wavelength and the slit width should affect it. Okay, what happens to the width and brightness of the central max of the diffraction pattern? Are we going to have the width increases? Hang on a minute, the slit width is increased. No, if the slit width is increased, you should be able to see, and you should know this anyway, that then you're going to end up with less diffraction happening. And you know that's the case because with an open door, light doesn't really diffract much as it goes through a wide open door. It only happens when it goes round or through very small gaps or around very small objects. So I don't think it's going to be A, I don't think it's going to be B. Let's have a look at C. Width of the central max decreases. What's going to happen to the brightness of the central maximum? Well, if the central max is more condensed now, as it were, then that means that the brightness will increase because the intensity is going to be increased. So it does look like it's going to be C. Makes sense, doesn't it? The more spread out the light is, the less intense it's going to be, and vice versa. Okay, we have a ball 45 degrees. That's nice. We've seen this question many times before. Ball reaches its max height after a time of 2 seconds. What is the displacement of the ball? Oh, interesting. That's not horizontal distance. I think they're looking for the total distance, or, as the crow flies. Okay, so it's going like that. So we need to think about horizontal and vertical. Vertical, we can go for suvat. S, we're going to need that in a minute. U, we don't really care about. Oh, yes, we do. That's a lie. We will in a sec. V is going to be 0 because it's reached its apex. A is going to be minus 9.81. And T, we're told, is 2 seconds. So let's find out U first. So just V equals U plus AT. Or rearranging that, that's U equals V minus AT. And so that's going to be just 0 minus 9.81 times by 2. I think we can ballpark this on, so I'm just going to say that's 20 meters per second. If it's 45 degrees, then if it's going 20 meters per second upwards, then that means it has to be going 20 meters sideways too. So we can know the horizontal distance. We'll deal with that in a second. First of all, we need to know the vertical distance. So S equals UT plus half AT squared, or we can go VT minus half AT squared. And so that's going to be half times 10 times 2 squared. And so in other words, it's going to be 5 times 4, so that ends up being 20 meters, funnily enough. Nice numbers going on here. So let's figure out the horizontal distance without air resistance. It's just going to be distance equals speed times time, horizontal speed that is. And so that's just going to be 20, like we said, times by 2, so that's going to be 40. So we have a triangle now, 20 meters upwards, 40 meters up there. And so therefore we want to know this distance here. And so that's going to be the square root of 20 squared plus 40 squared. So in other words, the square root of, what's that going to be, 2,000? That ends up being 45 meters. Cool. Question 19, object moving in a straight line, blah, 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 blah. Variation of momentum with time. Okay, momentum and time. Interesting. Gradient of the graph. Okay, so gradient, let's just put that there. Gradient is going to be equal to mv divided by t. And what is v divided by t? That's equal to ma. And so that should be force. And sure enough, that's one of the options. So I don't think it's going to be A or C. And area under the graph, well, we have mv times by t. And if we just think about v times t, well, that's just going to give us the mass times displacement, mass times distance. So therefore, I think the answer is going to be D. 20, what's a pair of vectors? A, weight, yes. Work, no. B, force and energy, no. C, displacement momentum, yes, because displacement is the vector version of distance. D, acceleration, yes. Power, no. 21, what statement is correct about a superconductor? Resistivity is small but not zero. This always confuses people. You think that resistance goes nearly to zero. No, it really does go down to zero. It is zero. What about B? A current in it causes no heating effect. That is true, because if there's no resistance, then, you know, IR and P equals I squared R, there is no energy wasted. C, its critical temperature is independent of the metal. No, very much dependent on what it is, because otherwise you could just make a superconductor out of steel, couldn't you? D, keeping it cold makes it too expensive to use. Well, I don't know about that, but it makes it very expensive to use, but it depends what you're trying to achieve. That's a bit of a rubbish statement, actually. 22, we have, this one. This confused a heck of a lot of people, if I remember rightly. So we have this bar, and it's being held up by a wire. Oh, we have a trapdoor, sorry. Oh, I haven't done a very good job here. That's okay. Not too shabby. Take that up a little bit, and then we have that. Okay, so we have arrows A and B and C and D. Now, this confuses a lot of people because free body diagrams with forces, which arrow shows the direction of the reaction force of the hinge on the trap door? So, what I like to think of in these kind of cases is what would happen if the reaction force disappeared? Disappeared. Ugh. Disappeared. Oh, I can't spell today. So what would happen if the reaction force and the hinge just completely disappeared? Well, we have this rope pulling the trapdoor to the left, but then also we have the trapdoor being pulled downwards due to gravity, don't we? So what would happen, do you think, if the hinge just disappeared? Well, I think that the trapdoor would do something like this. I think it would go down like that, because it would just go downwards due to gravity and it would be pulled to the left by the rope. And so if that's not happening because the hinge is there, then why is that? Well, it's because there is a force that is countering that other resultant force. And so I think the answer is B. 23. Resistive force is kV. What is the terminal speed of the sphere? Okay. Terminal speed of the sphere. So if we have a ball that's falling at terminal velocity, we know that we have the drag force pulling upwards is equal to mg. Therefore, we can say that kV is equal to mg. Therefore, V is equal to mg over k. Easiest question ever. What's the answer? It's A. 24. Trolley moves down a slope with constant acceleration. Mass of the trolley is doubled. Oh, dearie me. So mass is doubled. Okay, so A, the accelerating force is unchanged. No, that can't be true, can it? Because if the mass increases, then by definition, mg or mg sine theta, whatever, is going to increase. No, it's going to be acceleration that stays the same. The accelerating force is halved. No, because F is going to be proportional to m, so therefore it's going to be the opposite. It's going to have doubled. C, the acceleration is unchanged. Yes, A is constant because F equals ma, and of course if mg sine theta is the force and that's equal to ma, then therefore we know that the m's cancel, and A is just going to be dependent on the angle. D, the acceleration is halved. No, we know it's going to stay the same. 25, variable force acts on a mass. Okay, so boop, boop. There we go. And we have 10 and 20 and 0.5 and 1. What is the speed of the object when t equals 1 second? Easy peasy. We have a force time graph, and we know that the area under the graph will give us the impulse or the momentum gained. And if it's starting from rest, which it is, then we know that that impulse is going to be equal to the end momentum. So let's just figure out the area, shall we? So it's just going to be 10 times 0.5 plus, what's that, 20 times another 0.5. So actually that just ends up being 30 times 0.5. So that's just going to be 15 Newton seconds, or kilogram meters per second, same thing, if I can write it right. And we know that momentum is equal to mv, so therefore speed is going to be equal to momentum divided by mass. So that's going to be 15 divided by 2 kilograms, and that gives us 7.5 meters per second, and that is C, therefore. 26, heavy cable. Okay. Which graph shows the variation of tensile stress? We know that stress is proportional to force, and so therefore it's going to be proportional to the weight that's pulling down on it. Okay, fine. So we know that the stress is going to start off big, and we know it's going to come down because there's less wire beneath it pulling down on each bit when you go down. But there is a weight on the bottom, so it's not going to go down to 0. So if there was no weight on the bottom and it was just a wire, then it would go down to 0, but it's just going to do that. So it looks like our answer is D. 27, we have a mystery box of resistors. Which box gives the same reading on both ammeters? Okay, so we have that and that. Oh, well, this is pretty easy if you ask me. The only way that this is possible is if this is going to be a series circuit. So our answer is definitely going to be D. Of course, if you start to make it parallel in any way, because this one here is measuring the total current, if the other ammeter is in a branch, then by definition, the current in that one has to be different from the total current. 28, 2 circular discs. We have 2 meters apart. Oh boy, what is this? The air gun pellet is fired parallel. The pellet makes a hole in the discs. The holes are separated by an angle of 45 degrees. Speed of the pellet is 300 meters per second. Oh, this is a weird question. How many revolutions does each disc complete in 1 second? So we're looking for the frequency. Okay, so if the speed is that and the distance is 2 meters, then that means that the time it took to do that is going to be distance divided by speed. So that's 2 divided by 300. And if it's done 45 degrees in that amount of time, so that's for 45 degrees, or in other words, 1/8 of a revolution. So therefore, the time period is going to be equal to 2/300 times by 8. So that's how long it would take to do 8 lots of that 45 degrees. So that's going to be 16 divided by 300. But if we're looking for the frequency, frequency is equal to 1 over the time period. So that's just the reciprocal of our time period. So that's going to be 300 divided by 16. I think the answer looks like it's going to be 19. That's going to be A, isn't it? Yep. 18.75. So therefore, it's going to be 19. It's A. 29, we have a resistor dissipates 100 watts, and we have the PD is 25 volts. Okay, the supply output is reduced to 20 volts. Ugh. Oh boy. Okay. Let's just draw a quick diagram. It's basically just a resistor. So there's that. We have our R there. Supply output is reduced to 20 volts and the resistor is replaced. So the power dissipated is still 100 watts. What is a percentage decrease in resistance? Okay, we're obviously going to need our equation for power. It's going to be, well, we could use VI, but the problem is that we don't know how I is changing. So therefore we could use I squared R, but again, blah, blah, blah. So we're going to use what we have. We are dealing with R and we're dealing with V. So we're going to do V squared over R. So if P is staying constant, then that means that V squared is proportional to R, or in other words, R is proportional to V squared. V is going down to 20 volts, so that's going down to, what's that, 4/5? So times by 4/5, let's just say times by 0.8. And so therefore, V squared times by 0.8 squared, and so that is 0.64. So the new resistance has to be 64% of the original resistance. Therefore, the decrease must be the rest of that. That has to be 0.36 or 36%. And so I think the answer is B. Oh yes, finally. You never get questions on bank tracks and banking planes. I love it. Okay, I've woken up now. We have a plane and it is banking. And there's our theta there. There we go. R is over here, and that's going towards the center of that circle. And of course, we have mg going down there. That's nice of them to label that, because that gives us something that we need to know. Okay, so what is tan theta? Well, let's have a look at this first. So we know that mg has to be equal to this force pulling upwards, the vertical component of the lift. So therefore, we can say that, I tell you what, I should probably get rid of that. This is our force here. This is our big force, our upthrust, our lift. So therefore, we can say that mg is equal to whatever this force is times by cos theta. I'm multiplying by cos theta because I want to find the component, the vertical component. If you don't know where that comes from, then have a look at my easy vectors trick video. Way better than drawing lots of triangles. Figure it out. Hypotenuse, opposite, and adjacent and all that jazz. Trust me on that one. Okay, and so therefore we also know that the horizontal component of F is supplying the centripetal force. So we can say mv squared over r is equal to F sine theta. But we're looking for tan theta. You should remember that tan theta is equal to sine theta over cos theta. So therefore we're going to rearrange both of these for cos and sine. So we can just say that, oh, let's just do it all in one go, shall we? So sine theta is equal to, according to this equation here, that's equal to mv squared over fr, and then divide that by the top one there. Cos theta is equal to mg over f. M's cancel, f's cancel, and we just end up with v squared over gr. So it looks like the answer is D. Finally, 31, we have a double spring situation, and what quantity has its magnitude at a minimum value? Wait, what? Which quantity has a minimum value? Why couldn't they just say that? Okay, whatever. When the mass is at Q. Okay, so at minimum, question mark. A is the acceleration. No, because we have the greatest acceleration when we're furthest away from the center, minimum acceleration when we're in the center. So A max is at center. So therefore, that's not our right answer. B, the kinetic energy of the mass. Yes, EK min there, could be. Sounds about right to me. I think it's going to be B. Let's just check the others real quick. C, potential energy. No, because, well, if we know that kinetic energy is at a minimum, then potential energy certainly can't. We know that it's not moving at amplitude, so therefore, as per usual, EP min at center or at equilibrium. And D, finally, the resultant force of the springs on the mass. Again, that follows on from our acceleration, so it can't be D. So there we go, finally made it. It's a pretty tough paper, just you wait until you come across paper 2. It's even worse. But I hope you found this helpful. Leave a like and a comment if you did. And don't forget to check out my channel for other videos for A-level physics, including those going through whole papers in under an hour. I'll see you next time.